Welcome to Neural Networks with RubyFANN. I am Ethan Garofolo, your humble presenter here today. I own Big O Studios, order of complexity there. That's a consultancy up in Round Rock. Do web application in a Ruby-based web framework that must not be named because this is a Ruby conference, right? Also use Node.js, writing a book in that, and I do Unity 3D development as well. Sometimes that all is in the same project. And of course, I've got my super secret projects I can't talk about, but we all have those, right? Anyway, we're going to talk about neural networks today, obviously. Hitting on what they are in general, how they operate, strategies for how to apply them to the problems you might be trying to solve yourselves, how to apply them to some specific examples that we'll get into in the talk. Then we'll talk about other problems you could try to solve with a neural network, and then, of course, we'll have time for Q&A. So I do want to ask, how many of you here have formal computer science training? Like you went to school for it, you got a degree? Okay. Or you got some degree of exposure to it. I'm glad that wasn't all of the hands because chances are, if you did CS training, you probably got some exposure to neural networks, but we're going to review it anyway because it's really useful. And the one other caveat I want to give is people go to graduate school to study neural networks. They can spend 3-4 years doing that to get a PhD. I have not done that, and we're probably not going to get that deep of an understanding of neural networks anyway. We could try it, I suppose, but we'd probably be here until LoneStarRuby 2017, and I imagine that you all have better things to do in the meantime. So let's get into it. What are neural networks? They are function approximators. Boy, that really explains it, doesn't it? Two parts there, functions and approximator. You've probably seen functions before, right? I'm not talking about the function keyword in JavaScript or C++, the concept of mapping a domain to a range. And here's an example of one. That's the identity function. You probably saw that in high school even. Now, there are two things about the way we learned functions in high school. One, I kind of left high school thinking that all functions map numbers to other numbers. That doesn't have to be the case. It just maps domains to range values. Here, that's numbers, but what if my input was like a lolcat or something? As long as it also output a lolcat, that's still the identity function, right? The other thing was that when you worked problems in high school, you tended to you got an input, you got the function, you were supposed to calculate the output, or vice versa, you had the output and the function. What was the input that produces that? Well, in the real world, you don't always know what the function is, right? That's the role of a neural network. You have some set of observations, and you want to find what is the rule that takes me from this here to this over here. So we approximate that with the neural network. And why is that an approximator? Because they're very rarely 100% accurate. It's not an exact science. There is a lot of experimentation. Scott Bellware, who spoke earlier today, he spoke last year at Lone Star as well, and he gave a comparison of the engineering console in a submarine. I don't know if there's a single console in a submarine for engineering, but the point was that you have this infinite array of dials and switches and valves or whatever, and you can tweak all these little things to get the machine running just how you want to. Neural networks are kind of that way too. There are all sorts of little things you can tweak. And it takes experimentation to find what works. It takes experimentation to find out if it's even going to work for your problem. You don't even know that going into it, which is, great, right? So it's good to try to time box these investigations, I suppose. So how do they work? This right here is an example of what a neural network might look like. The circles are what we call nodes. And over on the left, where it's n sub I, and that doesn't show up very well, but that is I for input. Those are your inputs. You get to choose what those are, subject to the constraint that it has to be a numeric value. Whatever your input is, you have to somehow represent that as a number. And then over on the very right, you have output nodes. You're going to have one or more of those. Obviously, if you had no output nodes, what's the point of having the neural network? But there's no set number of them that you have to have. That just depends on your problem. Those things in the middle then are 0 or more what we call hidden neurons. Hidden in the sense that neither your input or output influences them directly. Now, in this picture, the 3 hidden layers there, they all have 4 neurons. They don't have to have the same number per layer of hidden neurons. That's up to you. But what they do is, if you can imagine, A neural network approximates a function, and functions can be graphed, right? Well, the more hidden neurons that you have, the more complicated of a graph your function can produce. Now, unlike in metal music, where more volume is always better, in neural networks, more hidden neurons are not always better. It really depends on your application. It depends on how much training data you have available. We'll talk about what that is in just a second. It depends on a lot of factors. So, input and training, I mentioned those a minute ago. The goal of a neural network is you have to train it to correctly recognize data. And the way that it works is when you first initialize a network, every one of those nodes is going to have some weight assigned to it. And that's weight in the sense of importance, not the, hey, wait a second type of weight, for those of you who aren't reading. So you have some corpus of training data where you have your observations and you know what the output is already, what you would expect. So you take some subset of those and you feed them into your neural network. And it's going to propagate through there and get to the end, and most likely it will be wrong for a long time. But there are algorithms that then go back and adjust that weight, and one of them is backpropagation, and it basically just takes all the error from the more right side of the of the network, and then feeds it back forward to help calculate the correct weights. So, I mean, there's complicated math behind that that's well beyond the scope of what we're doing here, but the gist of it is that it being wrong at first is okay. That's how it learns, kind of like, you know, how humans learn. If you've ever learned to walk, you probably made a lot of mistakes at first. So here's just like a pseudo-codey type example. If I were trying to teach a neural network the identity function, I would give it inputs of 1 with an output of 1, 2 and 2, 3 and 3, and so forth. And then ideally over time and iterations, the network would learn, oh, if they hand me 4, I should just produce 4 again. And that's great. Then you have a learned network, which you could go deploy to your production servers, just in case you needed to write an application that spit back exactly what people put into it. So now, how would you know how to apply a neural network to a problem, or whether or not you should? And like many of the answers I could give here today, it's really hard to give a recipe for doing this. I can give you one big gotcha to consider, a couple of them actually. The first one is more technical, and that is, let's say that your input is dealing with enumerated data. Let's say that for some reason, whatever, for example, one of your inputs is what type of food something is, be it Italian food, Mexican food, Korean food, I don't know. You pick it, right? Well, you have to reduce that all to some numeric input. And let's say you choose to do that on a single node. You might start assigning numbers to those different types of food. Like you might say Mexican food is 0, Italian food is 0.5, or whatever, right? So you've created sort of a scale there. But look out. You've just introduced information there that may not be correct. Whatever food you put at 0 to the network, it's going to be closer to whatever food is at 0.1 than whatever food is at 0.7. And that's a bias. Is it good, bad? I don't know. You'll have to experiment and find out. But the point is, you've told the network something about these foods that may or may not be true. One way to overcome that then is for an enumerated type, just give a separate node for each possible value and set it to 1 or 0. That's up to you. The other one is not a technical problem. I worked at a company called 7 Billion People, and the RubyFANN gem that we're going to talk about here was actually born from this company. And basically what we did was we were taking clickstream data on websites, using the actual words that people clicked on to try to infer things about the people, and then dynamically change the website to be more communicative with them. Have you ever been to a website, you're just like, I hate this thing, I'm not even going to read it, and you just shut it down without looking at it? Anyone? I've done that a bunch of times. We wanted to prevent that, and we had a neural network behind it in the second iteration. But the first time we just used a simple, what we called Inference Engine, and our CEO really liked the Inference Engine because it was predictable. He knew exactly how it operated. When you've trained a neural network, let's say even if it's 100% accurate and you save that off, do you know what you have? You have a text file with some numbers of how many nodes and a bunch of weights. So if you open that up, even if you're the guy who wrote it, and you look at that and you say, I got no idea how this thing works. If you're trying to secure investment dollars, it may not be the best way to go about doing that. So that, unfortunately, every problem that we solve, even though technical, is eventually a human problem. Keep that in mind as well. That may matter to you at your stage of whatever company you're at. So those are just some general things to think about. So now let's break it down into some specific problems I went at. The first one I did was spam detection in emails. Now, if any of you have ever worked in spam detection, you already know that neural networks are a suboptimal solution to that problem. So let's just skip that part right now and just say, hey, we are bent on using neural networks to solve this. How might we do it? This is where RubyFANN comes in. And RubyFANN is two things. Ruby, you should already know what that is, or else I don't know what you're doing here, especially on a Saturday. FANN is Fast Artificial Neural Network. It's a C library. That's its link. You can go check it out. It's great. RubyFANN then is Ruby bindings into that. That was written by a guy named Stephen Myers. He runs Tangled Path now here in town. It's a good guy, a friend of mine. So we would obviously need to get that onto our computer. And you can do that the same way you would install any gem. Gem install it, stick it in your gem file, or I don't know, however else you install gems. But those are the only two ways I use. So if you don't happen to have FANN installed on your system, RubyFANN will take care of that for you. It'll go grab the source, download it, compile it, and so forth. And if you've ever installed the Postgres gem, you might really like the fact that RubyFANN would take care of just installing its underlying dependency for you. Postgres has always given me problems, but I don't know. We all have different experiences. And I know this works on Ubuntu and OS X. Your mileage may vary on Windows. So I do have code up for these experiments. Yes, that does say TicTacToe. That's because I did two examples, and I did TicTacToe first. So the repository got named TicTacToe, not spam detection. So whatever. So let's say you were going to do it. You were going to build a spam detector using a neural network. Open to you guys. What inputs, what characteristics of an email do you think might indicate spam or ham? Yeah, that would be a great one to consider. You could like link it to the sender it came from and start growing a history there. Any other thoughts? You know, that's awesome. Who said that? Yeah. That Akismet does that. The great WordPress spam filtering plugin. You can link up to it as an independent API, and Ryan Bates did that in one episode of Railscast. And that's actually how you test if you've wired up to the API correctly. You put Viagra in there, and if it doesn't say spam, you know you did something wrong. But yeah, that's exactly. And going back to that original thing about enumerated data, that would probably be like a single node on or off. Did it have Viagra in there? So any other thoughts? Yeah, exactly. You've seen how many different things there are for what seems like a rather simple problem? I ended up with 82 different inputs. I didn't use the Viagra one or the addresses for this particular problem. It was inspired by an answer in Stack Overflow. But examples of what I did consider are character count, word count, alphanumeric character count, the ratio of alphanumeric characters to non, so like, links and stuff in there, because, it takes non-alphanumerics to make links. Other things that I considered in there was like how many words only appeared once, what was their ratio to the rest of the word count, and so forth. Just all kinds of stuff. And so I got a corpus of emails from that link up there at csmining.org. Great website if you're ever looking for data to mine, because they have lots of it. I processed that into a database, turning basically text into the relevant inputs. And that code is in the GitHub repo. I'm assuming that most people here have opened a file in Ruby, and that's about as complicated as that code gets, not really worth actually putting up on a slide. So if you want to find out how I did it, go to the repo. Now we get into the actual use of RubyFANN here. It has a class called train data in the RubyFANN module there, and you basically just give it inputs and the outputs that should be there, right? And those are parallel arrays. If you don't know what a parallel array is, it's essentially when you have one or more arrays, they're all the same length, and the nth element of each corresponds with one another. It's not enforced by the language or anything, and it can be kind of tricky to follow that if you're reading someone else's code, but that's the way the gem works. So here's an example of it. Those numbers I just made up to show that the ones are related to the ones, and the twos are related to the twos. And now all of our training data is encapsulated in one nice object, which in just a second, you'll see what we do with it. We actually create our network here using the standard class, and it takes a hash with 3 different key value pairs in it. One is the number of inputs. I already said that was 82, so that's why that number's there. The hidden neurons are an array where each element is how many hidden neurons go in that layer. So here the 0th element there is the first layer of hidden neurons. I put 5 in there. And this was rather arbitrarily decided. I did not do extensive testing on that. And in this particular example, there's only one output. Was it a spam or not, right? So that just creates the structure of our network. It still doesn't know anything. So we train it. By using our training data from before, we just call this train on data method here. And the other parameters, that number of epochs, that's just basically, you have your big chunk of data, right? And you need to run through it to train your network. That says how many times it's going to try to train itself to get within this error threshold before giving up. If it can't get to your desired error threshold before that number, it stops. And then that 10 is, if you're running this from a console, every 10th iteration it will output to the console how well it's doing. Now for what error threshold you want to have, that's domain dependent again. Like if you're doing something with tweets, more error might be acceptable, but if you're, say, running a space shuttle's launch or something, there's much less of a tolerance level there that you can have. So I wrapped that all up into a method and then tried training this, and it was really interesting seeing this. Check out these error numbers. That one in particular. So it was always wrong when it was trying to train itself. So why could that be? Bad inputs. I mean, obviously errors in coding it to generate the input to the neural network, but it could have chosen bad inputs. It could have been misclassified data. I'm not blaming CS mining. It's more likely I had bad inputs. But you know, this is a good thing to have, though, because then you can start analyzing, well, what went wrong? Is this the right solution? What else could I tweak? I could change the number of hidden neurons. I could get additional inputs. I could cut out some of the inputs and so forth. And so that was fun to see how badly that was doing. But then elsewhere in the code, I wrapped up into this classify emails that took all of my data that wasn't used for training. And I said, OK, now that we have a so-called trained neural network, let's test it against other emails and see how well it does. And the way I did that was when it was training, a positive 1 meant it was a ham, a negative 1 meant it was a spam. So as an example, when I actually gave it some new stuff to look at, it hovered right at 0, which was the network saying, I don't know. So in this particular example, it worked about as well as random guessing would. But hey, at least it did no worse than random guessing, right? So now going back to that earlier point, neural networks are not the right approach, where I define right as gives accurate results. There's an article by Paul Graham on that explains why and explains how Bayesian networks are a better choice for that. But I think it's useful here to see the process of breaking the problem down and so forth, and then seeing why it would fail, right? Because if you go to apply this, you may run into that same sort of issue. Any questions on the email side of it at this point? Like, yes, sir. Do you mean this? Yeah. Yeah, I'm not. I just assumed that meant it was getting it wrong a whole lot. So, yeah, maybe I could have just bit flipped it and called it a day. Yeah. What? There was some. I forget. There was some movie. No, it was an episode of Numbers, of all things, where there was this guy pretending to be a psychic, and they were doing one of those experiments where they hold up a card and say, "What suit is this card?" And he was saying exactly the opposite one every single time over 100 times just to antagonize Charlie Epps, but he was cheating and using a mirror anyway. So anyway, thank you for.
I had two small questions. One was you mentioned that you could remove inputs to try to alter it, but I'm assuming the weights vary from 0 to 1.
Yeah, I think they do.
So I mean, I guess it shouldn't it train itself to go down to 0
Yeah, neural networks are good at that. If you give it input that doesn't actually have anything to do with the solution, it will start to ignore that. So that probably wouldn't have that great of an effect on it to actually remove them, because it'll do it anyway.
The other question I have is the graph you showed looked like a weighted DAG, but I wasn't sure if it's actually.
Do you mean this one? Yeah.
I didn't. It looks acyclic, but I wasn't. But I think are neural connections that usually cyclic though? Sometimes, like, don't they have feedback loops?
They do. That was just more of a general structure picture. Yeah. Okay. Yeah, definitely in backpropagation, that's exactly how it works, that the errors in the later nodes are fed back into the previous ones to try to get it correct. Any other questions or anything on that example? Let me get back to where we were. All right, cool. So next problem, TicTacToe. I thought this was a cool one because we all pretty much understand what TicTacToe is. Unless you're from England, then it would be noughts and crosses, I guess is what they call it there. I won't try the accent because that won't work very well. This was a really cool problem, though, because I was able to take the same problem and model it with two different networks. The first one basically just considered the board state as is, where a -1 meant the opponent controlled it, a 0 was neutral, and a +1 was I control it. And then the outputs were, there were 9 of them, 1 for each square. And essentially it gave a fitness for that one. So whichever square gets the highest score is the move that you should take. The drawback to that approach was I was hand programming the examples. So the network was going to be no better at tic-tac-toe than I am. And in my opinion, the only perfect tic-tac-toe player is the one who doesn't play, as the movie War Games taught us. Great way to avoid thermonuclear warfare, but there are much better ways to pass your time. The second approach then, it considered the board state and then what move was taken given that board state, and then what the outcome of the match was given that state and that move. And it got some really cool results, which we'll get to in just a couple of slides. But this code here is going through that first one that just considered the current board state. And part of that, of course, was getting a CSV file into usable input. There is no actual object called thing that converts CSV, blah, blah, blah. That's just some presentational hand waving to say that part of the code doesn't matter for today. But same sort of thing here. That spit out, the thing that actually does that spit out a hash. So I'm not doing something different there. It was just a hash instead of local parallel arrays there in the function. So we get the training data. We get the network with the correct number of inputs and outputs. And then, of course, that same arbitrary number of hidden neurons. There's nothing magical about 5 and 5 at all. And then we train it. And so here was one of the interesting results. This is the state of the board. And then that's what, I didn't put this code in the first bit of slides, and I should have. But once you have the trained network, and that's what FAN is up there, to actually then generate output given a set of input, you just call the run method on it. So, I mean, that's pretty intuitive, I would say. But so given this state of the board, that's what it output. So its first choice was the center square, which you have to make sure that it isn't already occupied. But then its next best choice was this one, and it's X's turn. And so you're thinking, well, why didn't it win? Why didn't it go for victory? That was one of the observations I made. It was hard to train the neural network to block an opponent or seize victory. For whatever reason, it just didn't go for it very well. So then I ran a tournament. There was actually a third computer opponent which just randomly picked a square. Because going back to the spam detection thing, if you can't beat random guessing, then that's bad, right? So I pitted each opponent against each of the others and gave them both the chance to be X and Y. And so in a game of tic-tac-toe, the X player has a huge advantage. That's just the nature of the game. And so random would beat the board state only opponent most of the time. Well, okay, when there was a victor, player X tended to win against the random opponent, but there were a significant number of draws as well. But you see that even though the board state with result one was Y, it still won a whole lot. And then you can see how it breaks down. But what was really cool to see was the board state with result absolutely trounced the board state only player. He won every time whether it was X or Y. So I thought that was interesting. That probably has a lot to do with the fact that that opponent had a lot more data to learn from. To generate the data for that, I pitted two randoms against each other and played them 1,000 times. So it really got to have a lot of exposure to tic-tac-toe games, whereas the board state only guy had like 27 examples to go off of. And I don't know. It'd be kind of hard to learn tic-tac-toe after 27 moves, I suppose, if you're a computer. But I don't know. That was breaking that down. Pretty interesting. So going back to the fact that there are so many things you can tweak in neural networks, it's a really good idea to look at the RubyFANN documentation. And one page in particular of that, this shows up really poorly on the slide, and my apologies for that. But if you remember back to the graph, each of those nodes has an activation function on it that basically affects how it deals with the numeric inputs that come in. And for example, there's one that will squash all the data into the -1 to 1 range. Is that good or bad? I don't know. It depends on your application and the experimentation that you do. But every single one of these symbols is another option for an activation function that you could have. And you can tweak that on a per node basis. You can do it per layer of nodes, or you can do it for the whole network. So you really have no shortage of things to experiment with. And if you were really enterprising, you could probably just generate a big loop that would go through all of those and then spit it all out and find out which one works the best for you. But again, time box it, because that is the rabbit's hole of rabbit holes. So other applications that you could use neural networks for: facial recognition. It's been used for that. Handwriting recognition, driving. I read an example of like at Toyota. They were trying to help alert drivers whether or not they were about to have a collision. And they based that off things like distance to nearest objects and so forth. You could maybe even do gesture recognition, and not like, that kind of gesture, but the kind that you have on your smartphone or whatever. So one way you might do that is breaking your screen down into a grid. The blue dots represent where the first points of contact for each finger were, and then trace out the rest of the path. And then every single one of those squares could be an input to your network. Now, that's a whole lot of input, so maybe you'd do a larger resolution on there, not quite so fine. But I don't know. What do you guys think? If you were to take on one of these problems, what sorts of inputs might you consider? No. All right, then. Let's go back to the go forth and work much awesome, and happy coding, folks.